Let us consider a cantilever of length L subjected to a transverse load of F at its free end B. The cross section is assumed of B cross H. The bending moment of this cantilever is varying like this, where MA at point A is F into L, that is the maximum bending moment. If we consider a section X at a section 1, 1 at distance X from point B, then we can write down sigma X is equal to mx divided by I into Y, and sigma X maximum will be mx divided by I into Y max, or sigma X max is equal to mx over, we can write down here it as Zx, where Zx is equal to I over Y max, or it is 1 by 6 bh square. So sigma X max can be written as 6f into x divided by bh square. So if we see this, we just see that this sigma X maximum is directly proportional to x, as mx is directly proportional to x. So we can write down the maximum value of stress at x is equal to L by 2, for example, is 3FL divided by BH square, and sigma maximum at x is equal to L is 6FL divided by BH square. So using these two equations, we can see that sigma X at L by 2 is half of sigma X equal to L. We will designing a component or a cantilever on the basis of this. This will be used as design stress, maximum induced stress in design equation. So if we design on the basis of maximum induced stress at section A, which is fixed point, we can find out the dimension of B and H. Once the dimension of B and H are obtained, on the basis of stress here, so all other points will be overstrengthened. At any point, this induced stress, maximum induced stress is less. So this section is basically oversafe. So we want that this section, the stress at any section is uniform. There is no change. Whether we calculate stress at this point, whether we calculate stress at this point or this point, we want that stress must be constant. So this stress is constant only if the sigma maximum, sigma X maximum, we want this is to be constant, and this will be constant if this is constant if mx by zx is constant. So mx by zx will be constant only if if z is directly proportional to x. So if Z has to be directly proportional to X, it means therefore 1 by 6 BH square has to be directly proportional to X. Now we have two options, either B can be directly proportional to X or H square can be directly proportional to X. It means we can have either B directly proportional to X or H square directly proportional to X. So B directly proportional to X will give us linear variation, which is easier to obtain. So that is why we make a cantilever, we make this cantilever of this type of section. This is fixed end. Now here this is distance x. Now this is A, this is point B. So here Bx is equal to B into x by L. So we finally got a cantilever of this size where the maximum width is B and the cross section at any section, let us say this is the section, if I draw a cross section here, I will get this type of cross section where this value is Bx and this value is H. So this is what basically we got. If we have this type of cross section of any cantilever, this will be of uniform strength. That this we can see if I substitute this sigma x maximum is equal to mx by zx. That was our definition. That was our formula for evaluating sigma x. Now sigma x zx, we know it is 1 by 6 bh square. If I substitute the values, it is f into x, mx is f into x, this is 1 by 6. Here we write bx as x by L into b, and then it is h square. So we get x and x cancelled out. It is 6f divided by bh square. Now this value of sigma x, that is sigma x we now obtain, is equal to 6fl divided by bh square. This is independent of x. Independent of x. It means whatever may be the section, whatever may be the distance of the section from point B, we will be getting constant value of stress. So this is basically a beam of uniform strength. This particular beam is called beam of uniform strength, and we will be using beam of uniform strength for laminated spring, and that will be explained in next video. How we can use, why the graduations, why we reduce the length of the laminates in making a laminated spring. Thank you.